If math has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping. Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today, we have a special video for you, and it is Graphing Rational Functions Part 4, dealing with rational functions that have more than one vertical asymptote. And we'll be checking that out in just a second. Please go ahead and subscribe to the YouTube channel Fort Bend Tutoring and click on that bell icon so you can be notified when we are uploading new and fresh content. So go ahead and give us a thumbs up on this. Share the video with your loved ones, whether they be friends or family or competitive classmates. Well, all right. So here's a quick glance of the problems that we'll be doing in this video. That's right, checking out problem number 1, number 2, and number 3 of the video, just to give you an idea of what to expect from me. Oh yes, let's continue. So as a reminder, when you're dealing with rational functions, you're dealing with the form of f of x equals to p of x divided by q of x, where p of x and q of x are polynomials and q of x cannot equal to 0. That's right. You can't have 0 in the denominator of a fraction. It is undefined, and we want to avoid that at all costs. Let's continue. Here you'll see the parent function for a rational function in the form of 1 over x. So you should have an idea that most of your rational functions, especially your common ones, will have this form. And here is the parent function of 1 over x squared when you have a quadratic function in the denominator. Yeah, there you go. So those are two parent functions of rational functions that you should be familiar with. But this is what can happen between vertical asymptotes when you have more than one in one graph. So when you have more than one vertical asymptote, like you do in these examples here, notice that there are opportunities to have different shapes between those two vertical asymptotes. So for instance, you can have a parabolic shape as you do in these two diagrams here, or you can have a cubic shape. And trust me guys, many times, especially when you're dealing with the parabolic shape here, it won't necessarily be symmetric across any axes. Sometimes it's going to be a little lopsided. It won't have a perfect parabolic shape, which is why you definitely need to be careful when you're graphing these rational functions that have more than one vertical asymptote. Just be aware that they're not going to always have a perfect parabolic shape. It will not always have a perfect cubic shape between the asymptotes, but many times they look very, very similar to these shapes, and I wanted you to be aware of that. All right, let's move on. Well, what we want to do is remind you next of the steps to graphing rational functions. Step 1, go ahead and factor the function completely. You want to then identify any holes that may occur. You want to find your vertical asymptotes, especially important for this video today, and also find any horizontal asymptotes you may have, and find your oblique/slant asymptotes that may be occurring in the function. You want to identify the domain. You want to then find the intercepts and find any points on the horizontal asymptote or the oblique asymptote. Continuing on, you want to graph your asymptotes and intercepts, and you want to make an XY chart to fully flesh out the graph itself and graph your function. That's right. After that, that's when I prefer to find the range and then, of course, identify the end behavior of the overall function. All right, so let's go ahead and check out problem number 1. In problem number 1, we have f of x equals x plus 3 divided by x squared minus 4. Well, the first thing I'd want to do with this problem is rewrite it. Knowing that the denominator is a difference of squares, we can factor this difference of squares, and you better believe I got a video that goes over factoring difference of squares. That's right. Go ahead and check that out. I'll put a link right here. There you go. And in the numerator, we'll have x plus 3 divided by the quantity of x plus 2 times x minus 2. That's right. I like to put my positive sign before the negative one. That's right, because I'm an optimistic person. Yeah, that's what I like to do. So we have our factored form here. This is the factored form of our rational function. Then, noticing that I do not have any holes because none of these factors will cancel out with a factor in the numerator, then I can set my denominator equal to 0 to solve for the vertical asymptotes. And when doing that process, once you have your denominator fully factored, go ahead and set each individual factor in the denominator equal to 0 and solve for it. So I'll have x plus 2 equal to 0, and I'll also have x minus 2 equals 0, and then I'll be solving for each of these two equations. That's exactly what I'll be doing. And you can't stop me. Yeah, I know you're hoping to stop me, but you can't. You can't, yeah, because this video is pre-recorded. So here we have x equals -2, which is the first vertical asymptote that we just identified. And the second is x equals 2. So we are going to put red boxes around our answers because it keeps them safe. There you go. So these are the two vertical asymptotes that we have identified. And if you want, you can go ahead and show that this is our factored form of our original function f of x equals x plus 3 divided by x squared minus 4. Now, this OA and this SA that's written right here is referring to oblique asymptotes or your slant asymptote that you may have from this function. Well, because the degree of the numerator is less than the degree of the denominator. See, the degree of the numerator here is 1 because this is x to the first power. So you go by the highest exponent on your variable x there. And then in the denominator, the highest exponent is 2. So since 1 is less than 2, you will not have an oblique asymptote in this case. In order to have an oblique / slant asymptote, the numerator's degree needs to be 1 more than the degree in the denominator. And that's not the case. So that means that our oblique asymptote doesn't exist. We don't have one. We'll just say none. And then, of course, red box it. While we're at it, let's go ahead and identify the horizontal asymptote. So when we're dealing with our horizontal asymptote here, so because the degree of the numerator is less than the degree of the denominator, that means our horizontal asymptote is going to be y equals 0. So now we have the horizontal asymptote. And once again, it's going to be y equals 0 because anytime the degree of the numerator is less than that of the degree of the denominator, the horizontal asymptote will always be y equals 0. Yeah. So red box it. Red boxing it. All right, let's keep moving through the steps. The next thing that we'll want to do is identify the domain, keeping in mind that this is also x plus 3 divided by x plus 2 times x minus 2. We'll go ahead and make sure that we cannot get a denominator that has the value of 0. Remember that having 0 in the denominator of our rational function will make the overall function undefined, and we don't want that. So we'll start by saying that the first factor, x plus 2, cannot equal to 0, and our second factor, x minus 2, also cannot equal to 0. So when you solve for each of these, by solving for x, you'll find that x cannot equal to -2 and x cannot equal to +2. Knowing this, you can write your domain in interval notation like so. You'll say that the domain will be -∞ to -2 union -2 to +2 union 2 to +infinity. And this is going to be the domain of our function, ensuring that any value that we have for x does not create an undefined situation for our function. Red box it. Yeah, go ahead with that red box. There you go. Then, as far as finding your x-intercept is concerned, all you have to do is set the numerator equal to 0 and then solve for that. So that means I'll have x plus 3 equal to 0, and then solving for this by subtracting 3 to both sides, we'll find that x equals to -3. So as an ordered pair, our x-intercept will be -3, 0. So essentially what I did was I set the function equal to 0, and the only way you're going to get 0 out of this rational function is for the numerator to equal to 0. So as long as my value of x doesn't cause an undefined situation in the denominator, then all you'll need to do is set the numerator equal to 0 and then solve for x in order to find your x-intercept. Yeah, that's all you need to do. Red box it. Red boxing it. Next, we'll be checking out the y-intercept. For the y-intercept, you'll simply be plugging in 0 for all of the x's and then solving for y. In other words, you want to find out what f of 0 is. So we'll have 0 plus 3 divided by 0 squared minus 4, and this simplifies to give you -3/4. Yeah, that's what you get there. So, knowing that, let's go ahead and write this as an ordered pair, which will be 0, negative 3/4 for our y-intercept. So what we're doing, guys, just to remind you, is just breaking down every single aspect of graphing a rational function, finding all of our critical values and points, as well as just following this flow that I've given you since part 1, which allows me to ease my stress in graphing rational functions. I like to make this process simple. Red boxing it. There we go. Let's move on. So it's at this point that I think we're actually ready to fill in our XY chart. Yeah. So first of all, I already know that at -2, the function is undefined. I already know that at +2, the function is undefined. Things I know already. All right, and what I want to do for you is I want to come up with some values to the left of -2, some values in between -2 and +2, and some values to the right of 2 to make sure that our graph is as accurate as possible. So let's choose values like -3, -4. How about -1, 0, and 1, as well as 3 and 4. So what I did was I first of all started with the values that are undefined, aka the vertical asymptotes in my function. All right, so that's what I wanted to do first. I wanted to make sure that I was recognizing the fact that x cannot equal to -2, that x cannot equal to +2, and so I wrote those first on my x and y chart. Then I want to know what happens to values to the left of -2. That's why I chose -3 and -4. Then I picked values between the two vertical asymptotes, and when doing this, because we are aware of the fact that we could have a parabolic shape, we could have a cubic shape, which are the most common shapes between the vertical asymptotes. So that's why I know I needed to have at least 3 points within this space so that I can make sure that my graph is accurate. So I chose -1, 0, and 1, which is pretty much going to divvy up that area between -2 and 2. All right, so now all we got to do is just plug in these values to figure out what the y value is, right? So let us begin with plugging in -4. Plugging in -4, we'll have -4 plus 3, which is -1 in the numerator. And then in the denominator, you'll have 16 minus 4, which gives us 12. So this is -1/12 for our y value when we have x equals to -4. Plugging in -3, we end up with 0 in the numerator, and we would end up with 5 in the denominator. So 0 over 5 is just 0. Yeah. Then as we plug in -1 plus 3 gives us 2 in the numerator. And then 1 minus 4 is going to give us -3. So we end up with -2/3 for our y value when x is -1. Plugging in 0, we'll have 3 in the numerator. And then we'll have -4 in the denominator. Once again, that is going to identify your y-intercept. And when we plug in 1, we will have 1 plus 3 in the numerator. That's going to give us a value of 4. And then 1 minus 4 in the denominator gives us -3. So we'll end up with -4/3. Next, we'll be plugging in 3. 3 plus 3 is 6 in the numerator. And then in the denominator, you'll have 9 minus 4, which is going to give you 5. So you'll have 6/5. And because I hate improper fractions, let's go ahead and write this as 1 1/5. And we'll write this one as -1 1/3. All right, because I prefer to graph a mixed number than an improper one when I'm graphing. It just makes it easier for me. Plugging in 4. 4 plus 3 is 7 in the numerator. In the denominator, you'll have 16 minus 4, which is going to give you 12. So that's 7/12. So a little over half. All right. Well, with these points already fleshed out in our XY chart, let's start by graphing our intercepts as well as our asymptotes. So we know we have a horizontal asymptote of y equals 0. So that's going to give us this right here. So we'll have a vertical line at x equals -2. Let's see if we can get a straight vertical line here from Mr. Whitt. There we go. And then we have x equals to +2 for the second vertical asymptote. All right. Nice. Now that we have our asymptotes in place, we have our intercepts located at -3, 0. So notice how in this case, we actually have a point on the horizontal asymptote. Now this can happen from time to time. If you wanted to predict whether or not your graph was going to be touching the horizontal asymptote or slant asymptote, what you could do is simply set the original function equal to the horizontal asymptote or whatever the slant asymptote may be. And then that'll inform you whether or not you actually have a point on the function that also coincides with the horizontal asymptote or slant asymptote. All right. So for instance, we were doing exactly that when we solved for the y-intercept. We set our function equal to 0 and then we solved for it, which informed us that we actually do have a point on our graph that lies on the horizontal asymptote, which can occur from time to time. So you have to check it. Graphing the y-intercept, we're going to be at 0, -3/4. So that's going to be almost to -1. So I have a point right here. All right, so there's my point there. Then graphing the rest of the points that we found, we have a point at -4, -112, right underneath 0 at -4. Then we have a point at -1, -2/3. So that's going to be about right here. And then we have a point at 1, -1 1/3. It's going to be a little bit past -1 as we're looking at our y values here. Continuing on, we have a point at 3 and 1 1/5. So 3 and 1 1/5 is going to be about right here. Thank you. Next, we have a point at 4 and 7/12. It's going to be a little bit around the halfway point in between 0 and 1. There you go. All right. So as I told you guys before, sometimes the parabolic shapes between the two vertical asymptotes are not perfect. They're not symmetric across any axis. So therefore, you want to be hesitant when assuming that you're definitely going to have a parabolic shape between the two vertical asymptotes. So what I'm going to do here is I'm going to be a little cautious. I'm going to see what happens when x equals to -3/2 and also when x equals to +3/2. So let's see what happens there. So let's go ahead and extend out this XY chart, and we're going to plug in 3/2, find out what that is, as well as -3/2, and see what values that will generate for us. Once again, you want to be very cautious because it can be very tempting to assume the shape between the vertical asymptotes. So let's go ahead and check it out. So plugging in 3/2 into our function, our result will be approximately -2 and 57/100. Then plugging in -3/2, your result for y is going to be approximately -86/100. So at -3/2, for instance, we'll almost be at -1. So that's going to tell me that it's coming back down. All right. Whereas when I'm at 1.5 or 3/2, I'm going to be at -2 and 6/10 practically. So that tells me that I'm going to be about right here. That gives me a clear indication that we are going to have a parabolic shape between the two asymptotes. There you go. All right. So it's going to look similar to this right here. Yeah. Just like that. Then, graphing the other parts of our rational function, we should have the following. We're going to be going through the horizontal asymptote and then hugging the horizontal asymptote from underneath. And then on the right side of our rational function, we're going to be coming down. And since we don't have any x-intercepts on the right side of that second vertical asymptote, then I know it will never touch the horizontal asymptote. Therefore, as we approach positive infinity, it gets closer and closer to 0, but never touches 0 or goes through it. So here's going to be our graph of our rational function. So using the TI-inspired CXCast software, we're going to go ahead and type in our function. So I know that I can click this here, got me a rational function there, and then type in our function. We have x plus 3 in the numerator, and in the denominator we have x squared minus 4. All right, so let's make this happen and then hit enter. So this is the graph for problem number 1. Now, when it comes to the range, we can get very, very accurate by using calculus to assist us. But since I'm not going to be showing you that in this particular video, we're going to use the calculator itself to identify the max and min around these two parts here. So obviously we'll have a max here in this area right here. And then we should be able to locate a minimum value over here. So let's go ahead and check that out. So first of all, you'll start with menu, and then you want to analyze the graph, and let's go with our maximum first. That should be the easiest thing. So we're going to start here and then move over, and we're ending up with a max of -655 thousandths. So far we'll be able to say our range is from -infinity to 655 thousandths. So next we'll be finding our minimum value here. So let's click on menu. Let's go to analyze graph and then to minimum. And so let's start here and see if we can identify a minimum here. And it looks like we have already. Yeah. So let's take that here. There we go. There we go. So using our calculator, we were able to identify that we have a minimum value of negative 95 thousandths. So we have a gap between that negative 655 thousandths as well as the negative 95 thousandths. There you go. So in between here and here are values of y that our rational function cannot generate. Okay, and we needed to know that. Yeah, we definitely needed to know that. And it's hard to come up with these values without using calculus. So for you calculus students, you can use the relative extrema to identify where this maximum and where this minimum occurs. And other than that, you're going to be using the calculator to find the max and min. All right, so we got our range down. And now for the end behavior, you'll see that as x approaches negative infinity, y approaches 0. And as x approaches positive infinity, y approaches 0. So that's going to be the end behavior for our rational function here. So that pretty much covers everything, guys. And that is problem number 1. Red box it. We're going to red box that end behavior right here. Yes, we are. And we're going to red box the range. There you go. Look at that chicken scratch right there. There you go. There you go. I know you can write better than me. It's okay. It's all right. Before we get into problem number 2, I wanted to remind you guys that you can actually set up a paid online tutorial today with Fort Bend Tutoring. That's right. You can actually have me as your personal private tutor. You know what I'm saying? So go ahead and check us out at tutormemath.net, and you can set up a paid online tutorial today with me. There you go. That'd be fun, right? You and me just chilling, doing math, looking over some homework, you know, preparing for a test. Let's get back to the video. So here we have problem number 2. We have y equals 2x divided by x squared plus 2x minus 3. And you want to start by factoring. Yeah, you do. So we have y equals 2x all over x plus 3 times x minus 1. And this is the factored form of our rational function here. Looking for holes, we don't have any because none of these factors of x will cancel out. So there are no removable factors here. Therefore, no holes. Then when it comes to our vertical asymptote, all we have to do is set our factors in the denominator equal to 0 and solve for them. So you'll have x plus 3 equal to 0, and you'll have x minus 1 equals to 0. And then, of course, you'll solve for each. So that informs us that we have a vertical asymptote that is x equals negative 3, and we also have a vertical asymptote that is x equals 1. So these are our vertical asymptotes of our problem. And the factored form. Let's go ahead and red box that. There you go. As far as our oblique asymptote is concerned, you don't have one. Why? Because the degree in the numerator is 1 and the degree of the denominator is 2. So anytime the degree of the numerator is less than the degree of the denominator, your horizontal asymptote, not oblique, but horizontal asymptote, is y equals 0. So that's the horizontal asymptote, which means we do not have an oblique asymptote. All right, it's going to be one or the other, not both. So let's go ahead and red box it. That's right, red box for you and a red box for you. Enjoy that. Next up, looking at our domain, we are already aware of our factored form, and therefore setting up the domain should be as simple as setting the individual factors of the denominator not equal to 0. So therefore x plus 3 cannot equal to 0, as well as x minus 1 also cannot equal to 0, because that would generate a 0 in our denominator, which would make our rational function undefined. And you can't have that. You can't have that. So go ahead and subtract 3 to both sides in this first factor here. You'll find out that x cannot equal to negative 3, and adding 1 to both sides of your inequality, you'll find that x cannot equal to positive 1 either. So in interval notation, our domain is going to be negative infinity to negative 3 union negative 3 to 1 union 1 to positive infinity. All right, and that's the domain. Red box it. Red boxing it. Right here. There you go. When it comes to the X-Intercept, all you do is set the numerator equal to 0 and solve for it. So 2x equals 0. Divide both sides by 2. This is division principle of equality. Thank you. This is going to be x equal to 0 and done. So our ordered pair is 0, 0, 0, 0. That's the X-Intercept. Red box it. Thank you. Then for the Y-Intercept, you would be plugging in 0 for x and solving for y. So as I do that, I would have 0 in the numerator over 0 minus 3 in the denominator, which is just 0 over negative 3, which is 0. Okay? So 0, 0. There you go. So the origin is the Y-Intercept as well as the X-Intercept. One and the same. Moving on. So I always like to begin with what makes my function undefined, and that is negative 3. It makes it undefined. As well as positive 1 makes it undefined. And I want to find values to the left, middle, and right of my vertical asymptotes. So I'll be picking values like negative 4 and negative 5, as well as negative 2, negative 1, and 0, and 2 and 3. Now, we already found some intercepts along the way, right? So we know that at 0, that's where we'll have both the x and y intercept. So we already know that value, right? Then let's plug in some other values to flesh out this rational function. We'll start with negative 5. So with negative 5, I'll have negative 10 in the numerator over, that's going to be 25 minus 10 is 15. 15 minus 3 is 12. And this simplifies to give me negative 5, 6. All right. Plugging in negative 4, that gives me negative 8 in the numerator. Over, that'll be 16 minus 8 is 8, and then 8 minus 3 is 5. As a mixed number, this gives me negative 1 and 3/5. There we go. Then plugging in negative 2, you'll have negative 4 in the numerator. Over, that's going to be 4 minus 4 is 0. That's going to be over negative 3, so that's a positive 4/3, which is 1 1/3. Much love to the mixed numbers when graphing. Thank you. Plugging in negative 1, you'll have negative 2 in the numerator. Over, this is going to be 1 minus 2 is negative 1. And then negative 1 minus 3 gives me negative 4. So this gives me a positive 1/2. There you go. Next, we'll have 2 to plug in. So that's positive 4 in the numerator. Then we'll have 4 plus 4 gives me 8. And 8 minus 3 is 5. So that's 4/5. Plugging in 3, you'll have 6 in the numerator. Then in the denominator, you'll have 9 plus 6 is 15. 15 minus 3 is 12. So this gives me positive 1/2. There you go. There you go. Yeah, that's what you get. So now let's start with the asymptotes. We're going to have an asymptote at negative 3. So vertical line here at negative 3. And then you're going to also have one at positive 1. Vertical line there. Thank you. Then you're also going to have a horizontal asymptote of 0. That goes there. You're going to have a x and y intercept of 0, 0, the origin. It's going to be right there. So looks like we're going through the horizontal asymptote again. Once again, if you wanted to verify that, you simply set your original function equal to the horizontal asymptote or slant asymptote to see whether or not your graph touches those asymptotes. And in this case, ours does. It does. So let's plot our other points. At negative 5, we're at negative 5, 6. So at negative 5, I'm almost to negative 1. So that's a point there. Then I'm going to have a point at negative 4 and negative 1 and 3/5. So that's going to be negative 4 and almost to negative 2. Okay, so that's that. Then at negative 2, I'm going to have a point at 1 and 1/3. So negative 2 and 1 and 1/3 is going to be there. And then at negative 1, I'm at a half. Okay, that's right there. Thank you. That's pretty separated there. I don't think I'll need any additional points here. But remember, this is on your own shakiness. So if you feel shaky about it, you go ahead and get some other points that are closer to the interior of those vertical asymptotes. But I'm pretty sure this is going to have a cubic shape. Next up, we have a point at 2 and 4/5. So we're going to be at 2 and 4/5 is almost to 1. So I have a point there. And then at 3, I'm at 1/2. Yeah. Right there. Okay, well, based on our parent functions and the points that we have here on the graph, I believe that our graph should look like this. We don't have to worry about going through the horizontal asymptote there because we don't have any intercepts to the left of our vertical asymptote. Then between the two vertical asymptotes, you'll have a cubic shape here based on those points that we have. And then over here to the right of our second vertical asymptote, it's going to look like that. All right. So there you go. I think we're looking good as far as the graph is concerned. And because we have a cubic shape between the two vertical asymptotes, our range is going to be negative infinity to positive infinity. There you go. The end behavior, guys, we can go ahead and calculate that as well. As x approaches negative infinity, y approaches 0. As x approaches positive infinity, y approaches 0. So there you go. However, we're still going to use the TI-inspired CXCast software to verify our results. Yeah, let's go ahead and do that then. All right, so we will begin by typing in our function. That's right. So it's going to be a rational function, and we have 2x. In the numerator, in the denominator, we have x squared plus 2x minus 3. Okay, let's go ahead and hit enter there. All right, well, looks like we're good to go. Because this graph looks just like ours. So we did a good job, guys. Way to go. Way to go. Problem number 3. So with problem number 3, we have y equals x cubed minus x squared minus 9x plus 15 divided by x squared minus 4x plus 3. So the first thing we want to do is we want to try to find out this factored form. For our factored form, we'll end up rewriting our function as y equals to x cubed minus x squared minus 9x plus 15. That's right, even though you have 4 terms in the numerator and could very well try to use factoring by grouping, this is not factorable. So therefore, the denominator, it is factorable. We'll end up with x minus 3 times x minus 1. There you go. Now to set up our vertical asymptotes, you'll have x minus 3 equals 0 and x minus 1 equals 0. And from here, you'll be solving for x in each equation. For the first, you'll have x equals to 3, and then for the second, adding 1 to both sides, you'll find x equals 1. So those are going to be your vertical asymptotes, x equals 3 and x equals 1. And we have our factored form of our original function. Red boxing it. All right, just like that. Next, because the degree of the numerator is 1 more than the degree of the denominator, you will end up with a slant asymptote. Yeah. A slant asymptote. You're going to end up with one. So therefore, let's go ahead and divide the numerator by the denominator. You'll have x squared minus 4x plus 3 going into x cubed minus x squared minus 9x plus 15. We'll need to multiply x squared times x in order to get x cubed. So x times x squared is x cubed. X times negative 4x is negative 4x squared. And then x times 3 is 3x. And then you'll need to change the signs. That's right. X cubes will cancel out. You'll bring down a 3x squared. And this is going to be minus 12x and plus 15. X squared goes into 3x squared. That's going to be 3 times, right? So 3 times x squared is 3x squared. And 3 times negative 4 is negative 12x. And 3 times 3 is 9. Okay. And then you'll change the signs. So changing the signs, that cancels out, and you'll end up with a remainder of 6. And so all we want for our slant asymptote is this, that x plus 3. So we'll be writing that as y equals x plus 3 as our slant asymptote. That's what we have, y equals x plus 3. Done and done, son. Next up, moving on to our domain, we'll need to ensure that the denominator does not equal to 0. So the way we can do that is by making sure that our x minus 3 does not equal to 0, and the factor x minus 1 doesn't equal to 0 either. So solving for each, you should know that x cannot equal to positive 3, and that x cannot equal to positive 1. So therefore, our domain written in interval notation is going to be negative infinity to 1, union 1 to 3, union 3 to positive infinity. And this is your domain. Red boxing it. For this particular problem, because you don't have any rational zeros, and also because our numerator is not factorable, we're going to go ahead and use our TX Inspire CX Cast to identify the X-Intercept. So we'll begin with the graph of our function here, and we're going to set it up as a rational function, and then we'll type in x cubed minus x squared minus 9x plus 15. That's all in the numerator, and our denominator will have x squared minus 4x plus 3. All right, let's hit enter. So notice here that we do have an X-intercept. So let's go ahead and find out what that is by first of all hitting menu and then going to analyze graph, and then this time we'll hit 0. So going to the left and right of that, you'll see that we have an X-intercept at approximately -3 and 23/100ths. So that's what we have for our X-intercept using our calculator, because that was going to be quite challenging to find by hand. All right, there we go. And you know what? For future reference, let's go ahead and fan out of this, because I'm pretty sure this is not all of the graph. So let's go to window and zoom out. So let's make the center here. There we go. All right. So that gives us our function. So we are good to go as far as our X-intercept is concerned, and we have a good window of the graph. So let's get back to things that we can prove without a calculator, shall we? Looking at our Y-intercept. For the Y-intercept, you want to simply plug in 0 for X and solve for Y. So plugging in zeros for all of these X's in our original function, you'll have Y equals to 0 minus 0 minus 0 plus 15 all over 0 minus 0 plus 3. So this gives us 15/3, which simplifies to 5. So as an ordered pair, you have 0, 5 as your Y-intercept. So let's go ahead and red box that. Red boxing it. Just like that, guys. All right, and that does it for our X and Y intercepts as well as our domain. Next, we're going to come up with some points here in order to graph our function. So we already are aware that we have vertical asymptotes at 3 and 1. There we go. Let's extend that a little bit. So therefore, when X is 1, the function is undefined. When X is 3, the function is undefined. So what we want to do now is we want to find values to the left of 1. So we'll move to, let's say, 0 and -1. And we want to know what happens in between 1 and 3. So this is going to be, let's say, 3/2, 2, and 5/2. There you go. That's 2.5. And then as well as 4 and 5. Okay. So these are going to be the values that I would plug in to generate my Y values. So next, what we'll do is we'll go ahead and graph our slant asymptote as well as our vertical asymptotes. So the vertical asymptotes we have are going to be at X equals to 1. So I have a vertical asymptote here. I have a vertical asymptote at 3. So it gives me a vertical line here. And I also know I'm going to have an asymptote at Y equals to X plus 3. So that means I have a Y-intercept there. I would go down 1 into the left one and up 1 into the right one. Same thing here, same thing here, same thing here. And let's go ahead and do our dash line through those points. All right, so that's going to identify where my slant asymptote is. Okay, so we have our slant asymptote, we have our 2 vertical asymptotes, and then we want to flesh out our points here. And so what I'll do is I'll go ahead and show that once I plug in these X values, I'll get the following Y values. All right, so after plugging in all of our X values that we chose, we have the following Y values. So now let's go ahead and plot this. Starting out, we have -1, 2, and 75/100ths. So at -2, I'm at almost at 3. So it gives me a point right here. All right. Then I have 0, 5. 0, I'm at 5. That's going to be right here. Thank you. Then we have a point at 3/2 and -3 and 5/10. So that's going to be about right here. Okay. Then we have a point at 2, -1. So 2, -1 is here. And then we have a point at 2.5 or 5/2 and negative 2 5/10. So that's going to be about right here. Okay, so now that we have this, then we're going to be plotting the 4, 9. So at 4, I'm at 9. And then at 5, I'm at 8 75/100. So at 5, 8 75/100 is going to be about right there. Okay, so what does that tell me according to everything that we've learned thus far? Also keeping in mind that we have that point at negative 3 and 23/100. So that's going to be in this mix over here. So graphing our function, we'll have the following. We're going to have a graph that looks like this. All right, there we go. And we'll also have a parabolic shape here. Then up here, we'll have this going on. All right. So that is going to be our graph. Yeah, pretty much. And as far as the range is concerned, our range will be from negative infinity to positive infinity. So we don't have to worry about this gap here because eventually that's going to hit every value. So you'll have negative infinity to positive infinity, like so. And for your end behavior, as x approaches negative infinity, y will approach negative infinity. And as x approaches positive infinity, y approaches positive infinity. Okay, and that's going to be your end behavior as well. And to remind you that our graph is on point, thank you very much, we'll end up with this graph right here on our calculator. So that lines up just with what we have on our graph we did by hand. And we actually have our points to verify that our graph is correct. Amen, amen, guys. So that does it for problem number 3. Red, box it. All right, so that's our end behavior and our range and of course our graph. And ladies and gentlemen, that's going to do it for graphing rational functions part 4, graphing rational functions with 2 or more vertical asymptotes. Well, as always, please subscribe, like the video, and if you have any comments or suggestions, go ahead and leave those in the comments section. And as always, if you're able, please donate, as that helps us bring you more free math tutorials. And don't forget that if you want some one-on-one tutorials with me, Mr. Whitt, and Fort Bend Tutoring, go ahead and check us out at tutormemath.net. And as always, peace.
Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutormemath.net. And set up a private tutorial with me and FBT. Oh yeah, baby.